Okay, so we start with problem 8, which is essentially converting things into either numbers or trigonometric values into e to the I beta, or simplifying them pretty much. So we started with a, which is just 1, and now 1, of course, 1 is e to the I times 0, because which equals e to the 0, which equals 1. B, so sine beta minus I cosine beta to the power 11. Now notice that e to the negative I beta is cosine beta minus I sine beta. This here, the sine and cosine are reversed. So I substituted in the identities for sine and cosine and simplified. So here we multiplied I and the numerator and denominator of this fraction. So then the e to the negative I beta is canceled right here. And then you just get 2 e to the I beta over 2i to the power 11 equals e to the I beta over I to the power 11, because the 2's cancel right here, which is just e to the 11 I beta over I to the power 11. C, we started with 1 over square root 2 over 2 times cosine beta minus I sine beta cubed. So we simplify the fraction of the denominator. We then substitute e to the negative I beta for the cosine beta minus I sine beta. So then we and since e to the negative I beta is in the denominator in this fraction, we move that to the top as a positive exponent. So 2 over square root of 2 e to the 3 I beta. D, I didn't have room for the start of the problem, but it was square root of 3 over 2. That's the cosine. And this is a minus I times 1 over 2 sine beta, and all to the power 7. So we simplified. The i's cancel in the denominator sign and the I in front of it. Those cancel. The 2's multiply out. So we have 1 over 4 times, and then we essentially group like terms. So square root of 3 minus 1 times e to the negative I beta comes from this term and this term. So we group those like terms. We simplified out the negatives. It's still the power 7th, and then we distributed the 7th power. So it's 1 over 4 to the power 7 times the whole square root of 3 minus 1 to the power 7 times e to the 7 I beta plus square root of 3 plus 1 to the power 7 e to the negative 7 I beta. Okay, so for 28, we were essentially showing that this transformation works. For this rectangle, we're transforming it through f equals e to the z as a half circle. So what we do is we consider the line segment x equals x sub 0 inside S. Now points in that segment have the form z equals x sub 0 plus iy, where 0 is less than or equal to y and is less than or equal to pi. Now, for these z, e to the z equals e to the x sub 0 times e to the iy equals e to the x sub 0 times cosine y plus I sine y. Now the cosine y plus I sine y makes a semicircle, and the e to the x 0 is the radius of the semicircle. Now, so when you have x sub 0 is 0, you get e to the power z equals e to the power 0 equals 1, so it's just cosine y plus I sine y. When x is approaching negative infinity, you get e to the power x sub 0 approaching infinity, but doesn't touch infinity, so you have the whole f0. But it fills in the semicircle.
We're doing problem number 34 for section 1.5. Our goal here is to linearize this in the middle, cosine beta to the 5th, and then solve the integral of that. First and foremost, what you're going to do is you're going to take cosine theta to the fifth, and you're going to substitute in the identity, which is e to the I theta plus e to the negative I theta over 2. Then you're going to take that amount on the inside to the fifth power. However, seeing as we have limited space on the board, I did the first step here of how that's going to go, just to show you the process. E to the I theta plus e to the negative I theta over 2 times e to the I theta plus e to the negative I theta over 2 equals e to the 2 I theta plus e to the negative 2 I theta plus 2 over 4. You carry that out, all the steps in the middle of multiplying this to the fifth, and you eventually get e to the 5 I theta plus e to the negative 5 I theta plus 5e to the 5 I theta plus 5e to the negative 5 I theta plus 10e to the I theta plus 10e to the negative I theta over 32. Your next step would be to break up the different components of that so that we can eventually substitute in for our identities. You've got e to the 5 I theta plus e to the negative 5 I theta over 32 plus 5e to the 3 I theta plus 5e to the negative 3 I theta over 32 plus 10e to the I theta plus 10e to the negative I theta over 32. We substitute out 16 there. We'll get 1 over 16 times e to the 5 I theta plus e to the negative 5 I theta over 2 plus 5 over 16 times e to the 3 I theta plus e to the negative 3 I theta over 2 plus 10 over 16 times e to the I theta plus e to the negative I theta over 2. We can substitute in now. So I'll have 1 over 16 times cosine of 5 theta plus 5 over 16 times cosine 3 theta plus 10 over 16 times cosine theta. Now that we have this, we can actually go back in and integrate. So we have the integral of 1 over 16 times cosine 5 theta plus 5/16 cosine 3 theta plus 10 over 16 cosine theta d theta. We can, using integral rules, go ahead and do 1 over 16 times the integral of cosine 5 theta d theta plus 5 over 16 times the integral of cosine 3 theta d theta plus 10 over 16 times the integral of cosine theta d theta. And eventually we'll get the solution of 1 over 16 times 5 sine of 5 theta plus 5 over 16 times 3 sine of 3 theta plus 10 over 16 sine of theta plus c. Because as is a rule, the integral of cosine is sine, and since there's a number on the inside of there, it's going to be divided by that. So it would be 1 over alpha sine alpha theta is the form. And eventually we get 1 over 80 sine of 5 theta plus 5 over 48 sine of 3 theta plus 5 over 8 sine of theta plus c. And that is our answer to the problem. We're doing problem number 2 from section 1.6. Letter A, the first part would be to find the cosine of this via the identities of cosine, and then we're going to verify it via the Cos-Cosh equation identity. So what we're going to do is going to do cosine of z being equal to pi over 4 plus I pi over 4 equals e to the I pi over 4 plus I pi over 4 plus e to the negative I pi over 4 plus I pi over 4 over 2 equals, if you multiply that I out to the exponent, you'll get e to the pi over 4I minus pi over 4 plus e to the negative pi over 4I plus pi over 4 divided by 2. You can substitute in now using exponential rules, and if you go ahead and do that, you get e to the negative pi over 4 times cosine pi over 4 plus I sine pi over 4 plus e to the pi over 4 times cosine negative pi over 4 plus I sine negative pi over 4. Now if you just change that around, you can get this portion to be equal to e to the pi over 4 times cosine pi over 4 minus I sine pi over 4 using trig rules. You get then in this situation you can substitute out via algebra, and you can get e to the negative pi over 4 plus e to the pi over 4 over 2 cosine pi over 4 minus I sine pi over 4 times e to the pi over 4 minus e to the negative pi over 4 over 2. And that'll get you the equation, the Cos-Cosh equation, which is what we were supposed to verify via this problem. So you get cosine pi over 4, cos pi over 4, minus I sine pi over 4, sinh pi over 4. Now, is the second part of problem number 2 from section 1.6. We're doing sine of z. As you remember, z equals pi over 4 plus I pi over 4. So you can do sine of z using the identity equals e to the I times pi over 4 plus I pi over 4 minus e to the negative I times pi over 4 plus I pi over 4 over 2i. That'll get you e to the pi over 4, pi over 4i minus pi over 4 minus e to the negative pi over 4i plus pi over 4. And if you do a little bit of algebra there, you can get I to the negative 1 times pi over 4, e to the pi over 4 times cosine pi over 4 plus I sine pi over 4 minus e to the pi over 4 times cosine negative pi over 4 plus I sine pi over 4. And do the same deal we did in the previous part. You get I to the negative 1 times e to the negative pi over 4 times cosine pi over 4 plus I sine pi over 4 minus e to the pi over 4 times cosine pi over 4 minus I sine pi over 4 over 2. Now, if you do a little bit of algebra over here, you can go ahead and get cosine pi over 4 times e to the negative pi over 4 minus e to the pi over 4 over 2 plus 2i plus I sine pi over 4 times e to the pi over 4 plus e to the negative pi over 4 over 2. And that'll get you our others, the sine sinh identity, which is sine pi over 4 sinh pi over 4 plus I cosine pi over 4 cos pi over 4. So we have verified that this equals this.
Okay, so for problem 16 in section 1.6, we're showing that we're taking this region in the normal xy plane and showing that f of z equals sine z transforms it to this region in the uv plane. Now what we do is we consider a line from the line horizontal line at y equals y0, and for x from negative pi over 2 to positive pi over 2. And now that's the z, for that z equals x plus I times y0. So then u plus iv, that's in the transform plane, is sine x plus I times y0, which is sine x cosine hyperbolic y0 plus I cosine x sine hyperbolic y0. Now, what we do is we set the real parts and the imaginary parts equal to each other. So u equals sine x cosine hyperbolic y, and v equals cosine x sine hyperbolic y. Of course, we don't include the I part. Now, when y is 0, we simplify and we get the line from this line from negative 1 to 1. But which is fairly uninteresting, so we don't really do much with that. But it just shows that where u is 0, there is something. It's not undefined. But for the other part, we use for when y is greater than 0, we'll say that we can solve for u, or solving for sine x. So in terms of u and cosine hyperbolic y. So we do that right here. So u over cosine hyperbolic y0 is sine x, and v over sine hyperbolic y0 is cosine x. So then we use a trig identity that says sine squared theta plus cosine squared theta is 1 to say that u over cosine hyperbolic y0 squared plus v over sine hyperbolic y0 squared is 1. And that gives you the u-intercepts of plus and minus cosine hyperbolic alpha, and the v-intercept of the positive sine hyperbolic alpha. Now we have to remember that there is a part of the original function that is with the y less than 0, right over here. So essentially, when we simplify that, it's almost the same thing, except it has the v has v over sine hyperbolic y0 equals negative cosine x. So you'll end up with the exact same u-intercepts, but the v-intercepts will include a negative sine hyperbolic alpha. So then you get the lower part of the ellipse from this. And of course, the insides of the ellipse are produced by concentric ellipses that are with y0 is less than I alpha.
We're doing problem number 34 from section 1.5. Our goal is to linearize and then solve the integral of cosine of theta to the fifth. First, you're going to go ahead and substitute in cosine theta for its identity right there. And then our next step would be to multiply out the fifth right there. And there's a lot of math involved in the middle here, and I didn't really have enough room to put it all down. So I did the first step right here, and we got that. Then as you continue down, you're going to go up here, and this is what you'll get at the very end. E to the 5i theta plus e to the negative 5i theta plus 5e to the 3i theta plus 5e to the negative 3i theta plus 10e to the I theta plus 10e to the negative I theta over 32. That is your solution for that. Now, you're going to go ahead and take that and break it up into some components so we can get a cosine back in there eventually. So you're going to break it up into like exponential components there and break it up into fractions. And if you do a little bit of pulling out here, you'll get 1 over 16 times e to the 5i theta plus e to the negative 5i theta over 2. Plus 5 over 16 times 3 to the I theta plus e to the negative 3i theta over 2, plus 10 over 16 times e to the I theta plus e to the negative I theta over 2. And you're going to go ahead and take that and substitute in. You'll get 1 over 16 times cosine 5 theta plus 5 over 16 cosine 3 theta plus 10 over 16 cosine theta. And now that you have this, you can go ahead and get your integral down here. So you'll have the integral of this up here, d theta. You'll eventually get, if you break it up using integration rules, you'll get 1 over 16 integral of cosine 5 theta d theta plus 5 over 16 cosine integral of cosine 3 theta d theta plus 10 over 16 integral of cosine 5 theta d theta. And if you solve that, of course, the integral of cosine is sine. So you'll get, and it's going to be 1 over this value right here.